Thanks for listening to this lesson on Fourier series. And before I even start with the material, I want to give you two introductory messages. The first is that there are a lot of mathematical details in here, and I'm going to focus on concepts and go rather quickly through the calculations. Just remember, you can always pause this recording and take some time to really think through those details, if that helps you. The second thing is that these concepts are really best understood when you work with them. So it's crucial for you to spend some time with some mathematical software program, Mathematica or something else, actually constructing Fourier series and plotting them and seeing what they do and what they look like. That's a very valuable exercise that we won't do in this recording, but that's really crucial for you. So let me start off and talk about what are Fourier series for. And they're a series description of periodic functions or functions defined on a finite interval. And we'll come back to that later. I want to contrast them with Taylor series, which you've studied previously. Taylor series are made up of polynomial terms. They have things like x's, x squareds, or if they're centered around a point other than x equals 0, you see terms like x minus a squared, and so on. And what Taylor series do is approximate a function focused around a point, the point A, about which you compute all the information that goes into the series. So this is called a local approximation. It's really good near that point you expand around, and not so relevant far from that point. In contrast, Fourier series are made up not of polynomial terms, but they're made up of trigonometric terms, sine and cosine. And what they do is they approximate a function globally, meaning across an entire range, rather than focused around a single point. And you'll see how this works in a moment. So how does it work? What you begin with is a function f of x that you're interested in, and you begin with an interval. And I'm going to call the interval minus p over 2 to p over 2. So that's an interval of length p centered around 0. If your interval isn't centered around 0, you can always translate your function so that it is centered around 0. And whatever the length of the interval is, we're going to call that p. Then you do some Fourier series magic on it, and what you get out is some coefficients, expressions for some coefficients. And I'll call these a0, ak, and bk. And these are coefficients in an infinite series that I've written down for you here. It has a constant in front, a0, plus the infinite sum from k equals 1 to infinity of ak cosine of this business plus bk sine of this business. And something to notice here is that 2 pi k over p is the angular frequency, or sometimes we'll just say frequency, of this trigonometric function. And the lowest frequency is when k equals 1. The frequency is 2 pi over p. And higher terms in the series for larger values of k give us integer multiples of that lowest or fundamental frequency, 2 pi over p. And those higher frequencies we sometimes refer to as higher harmonics. That's just good vocabulary to be familiar with. Here's how we derive those coefficients that you want to have in the Fourier series expansion of the function. We're going to start with the definition of the Fourier series, that's right here. And in order to find a0, what I'm going to do is integrate both sides of the equation across the interval. So that's from minus p over 2 to p over 2. So this equation here is just performing that integration. And to get to the next step here, I'm going to use the fact that for well-behaved functions, I can interchange the order of integration and summation. So here I have the integral of a sum. Down here, I've gone to having the sum of an integral. And there are some technical points that you might address more in a real analysis class, but for now we're going to assume that we can do that. Next, I'll attempt to evaluate these integrals. So let me go back for a moment. On the left-hand side, we're just going to keep this expression, integral of f of x across the interval. For a0, from minus p over 2 to p over 2, that's just a constant. So I should get out a0 times the length of the interval, which is p. For these cosine and sine terms, it's a very straightforward integration, and what you find out is that because of basically the symmetry of the problem, you come up with 0 for every integral within these summation terms. So you can just do that integration by hand, and when you do, you get the integral of f of x across the interval is a naught p plus 0 plus 0. Solving for a naught, you find it's equal to 1 over p times the integral of f of x across our interval. Okay, so that's a recipe, right? If you tell me your interval, and if you tell me f of x, I can now tell you what a naught is. Now we have to worry about the ak in the series, where k is bigger than 0. It goes from 1 to infinity. So these are the coefficients of the cosine terms. And what we're going to do is we're going to start with equation star, that was this original definition of the Fourier series, and we're going to do something similar to what we just did, but rather than just integrating both sides of the equation, we're going to multiply by something, and we're going to integrate. And since we're interested in cosine terms, what we're going to do is multiply by cosine of 2 pi jx over p, where j is another integer, and we're going to, again, interchange the order of integration and summation. And if we do that, we get this equation here, okay? And I won't read it out loud, but you can look at it, and there's a couple things to notice. Within the second summation, the one that has the bk's, you can show through direct integration that when k and j are integers, the integral of this sine term times this cosine term turns out to be 0. You can do that by hand or using Mathematica. For the first term here, we have two cosine terms. One has a k in it, one has a j in it, and we're thinking of there being a sum with the k's changing, the k's ranging from 1 to infinity. For all the values of k, when k is not equal to j, this integral turns out to be 0, and you can again do that by hand. However, if j happens to equal k, then what we really have here is the integral of a cosine squared term. Cosine squared of 2 pi k x over p. And what that integral turns out to be is p over 2. You can again do that directly by hand or using Mathematica. And I'll say that for brevity, I've neglected to write the limits of integration, but it's always minus p over 2 to p over 2. Okay, so what this does for you is it gets rid of this entire term, these are all 0, and it gets rid of the summation for you here. Almost all of the terms here are 0, except for when k and j happen to be equal to each other. So there's only one term in the summation that turns out to be non-zero. Also, this first term turns out to be 0 because of symmetries. And when you use all of those facts, what you come up with is that the integral of f of x times this cosine 2 pi kx over p dx is equal to p over 2 ak. And you can rearrange to solve for ak. You find it's 2 over p times the integral of f of x times this cosine term from minus p over 2 to p over 2. So again, you have an infinite series, and you would perform this integral to find each a sub k. For a sub 1, you would substitute k equals 1. You'd perform this integral. You'd get out a number. That would be a sub 1. Then you would do the same thing for k equals 2. You'd find a sub 2, and so on. Now, you do the entire procedure again, but instead of multiplying through by cosines, you multiply through by sines. You come up with the expression for b sub k, the coefficient of the sine terms, and it's very similar. What does this all mean? There's a lot of calculus, a lot of turning the crank, but don't lose the big picture. These formulas give you a way to approximate or express a function in terms of trigonometric functions, sine and cosine. That is, if you choose your interval and you know f of x, you can compute the ak and the bk. So let's do an example to try to make this concrete. I'm going to take a classic problem, which is the square wave. Okay, so this is 0 between minus 1 and 0, and it's 1 between 0 and 1. So the length of our interval here is p equals 2. Okay, and this is called the square wave function. We would like to compute the Fourier series. So here's how we do it. A naught is 1/2, that's 1 over p, times the integral from minus p over 2 to p over 2. So that's minus 1 to 1 of the function. Okay, so you got to integrate the function and multiply by 1/2, and you can just go back and look at the picture. If you think of area under the curve, the integral of this thing is 1. When you multiply by 1/2, you find out that a naught is equal to 1/2. All right. Then we'd like to find the a sub k for k greater than or equal to 1. So it's 2 over p times the integral across the interval of f times 2 pi kx over p. And if you turn the crank and just do the calculus, you find out that those are all equal to 0. Okay, then we can compute the bk, and it's 2 over p times the integral across the interval of the function times sine 2 pi kx over p. And if you turn the crank, you get an expression that's minus 1 over k pi cosine pi k minus 1. And what cosine pi k is depends on whether k is even or odd, right? Because when k is odd, like the number 1, you get cosine of pi. That turns out to be minus 1. Minus 1 minus 1 here is a negative 2, and you get minus signs canceling out. On the other hand, when k is an even number, cosine is equal to 1, and 1 minus 1 is 0. Things cancel out. So the sequence of the b sub k that you get is something like 2 over pi 0, 2 over 3 pi 0, and so on. So what does this tell you? It tells you that f of x is approximated by the Fourier series 1/2, that's a naught, plus, then all of the a sub k terms are 0. Then we have to do the b sub k terms. So it's 2 over pi times sine pi x, right? That's 2 pi kx over 2 when k is equal to 1, plus 0, plus 2 over 3 pi sine 3 pi x, and so on. Okay, so that's how it works for an example of the Fourier series. Like I said, it's much more elucidating to actually go into a program like Mathematica and start making plots. Thanks for listening.